Good morning to everybody. Welcome to our plenary sessions of this morning. I would like to welcome all of you. Of course, this is our last day, so we hope that you have been enjoying our conference and all the events associated with the conference. And well, let's start first with our first plenary, which is to be given by Professor Paulo Monteiro of the University of Aveiro. Professor Paulo Monteiro is an associate professor at the University of Aveiro, Portugal. In the moment, he's the research coordinator of optical communication systems and networking at the Institute of Telecommunications, which is an institution of Portugal, which has also location in Aveiro. And he's also the director of the Electrical and Computer Engineering course at the University of Aveiro. Professor Paulo Monteiro has held various positions, including position as the head of research for optical networks at Siemens from 2002 up to 2007 in Portugal, and then also for Nokia Siemens Networks, also in Portugal from 2007 until 2013. And from 2016 up to 2023, he's then working as director of scientific committee, member of doctoral programs in the telecommunications of the University of Aveiro. So I'd like to come to the stage Professor Paulo Monteiro, who is also a long collaborator and friend of me. So, Professor, please, the stage is yours.
And thank you very much for Sean for the introduction, and thank you very much for the invitation to be here. I'm very glad, and I'm really enjoying to be here. So I'd like to start my talk about optical wireless technology, unlocking multi-terabit wireless connectivity. So let me only first make a short introduction about the Institute of Telecommunications. The Institute of Telecommunications is in Portugal. We have different facilities. I'm here, most important, okay, you have Lisbon, Porto, Aveiro is one of the most important facilities that we have from IT, Institute of Telecommunications. So telecommunication is a non-profit organization, it's for public utility, and also it's associated laboratory since 2001. So the idea is to create dissemination, support advanced training, promote technology transfer, and support public policy. So only let me give a short introduction about Aveiro. So Aveiro city is in north of Portugal. So it's a small city. We have approximately 81,000 inhabitants. So it's here. What we call this Ria da Aveiro because it's salt water, so it's connected to the sea, to Atlantic. So these are only short, small pictures about Aveiro, and also from our coast. And this is some houses, typical houses from Costa Nova, which is near Ospora. So we have here our university campus. Okay, it's not all university campus because it's growing in other direction. But approximately we have 15,000 students, approximately 1,000 professors and more than 500 researchers. IT, we have 2 buildings IT this year. It's not, so they are in this region that we have two buildings of Institute of Telecommunications. Okay, so I'll show here, this is what you call the part of the salt water that in past was to produce salt. So what are our main research of optical communication systems and networking? So we've been working in high-capacity optical fiber systems, all direct detection, current detection, digital signal processing for optical communication system, advanced modulation coding, and non-linear modeling and mitigation. And also been working in high-capacity optical wireless systems for free space optics, and also related to visible light communications, and optical networking, part of the conversion, fixed mobile conversions, radio over fiber systems, and also the integrated communications and sensing. So we have been working part of the radio communications and LiDAR communication, also including LiDAR communications and also radio with communications. And also in current, we have now leading a European project, which have been working current MIMO radar network enabled by photonics. So today I'll be focused more on this part of high capacity optical wireless systems. So in part and also some part also optical networking. Okay, so this is, we have four postdocs, 10 PhD students, and 10 MSc students. So we still are not a very big group, but not a small group. So what, let me also talk about the first introduction about conversion of fiber and optical wireless communications for next generation of access networks. Okay, I'll show this picture here. So now we have to think not in 2D, but in 3D communications, some from the old terrestrial communications, but also we should also talking about in another dimension, in a part of also in a part of the space communication, inter-satellite communications, and also from ground stations to satellite communications. This is for outdoor communication. For sure, also we have all the fiber infrastructure, and also for indoor, we also need to talk about also from Wi-Fi. And also, we also talk today about VLC, how we can compete with Wi-Fi. Why now? Let me start from indoor wireless. Why indoor wireless is so important? Okay, it's very, for sure, 80% of the data connection is in the room. And also, people spend between 80 and 90% of their time indoors, unfortunately. And also, 70% of mobile phone use also in home. So indoor for sure it's a very important communications. But you know that all the bands for sub-6 GHz and also for millimeter wave, they've been congested. So we need to also think another spectrum. And it comes the optical spectrum from infrared until ultraviolet. So for sure, so optical wireless communication emerged as a viable alternative, and we have the part of free space optics that we will also discuss today, and also we have the visible light communications and ultraviolet communications. Okay, ultraviolet also is one possibility, but for sure is more dangerous for humans, and also you don't want to use inside skin protectors or glasses. Sunglasses, so I think that the two most important now should be the part of the visible light communication and free space optics in infrared. Visible light communication, so it has been started as attract more interest because of high capacity and also for secure wireless communications. This is also will show today the importance. And also we can also try to reuse the implement lighting infrastructure for lighting and also for communication. This is also we have been shown today. So what are the typical VLC modulation techniques? For sure, the most usually it's modulation of intensity of light using direct detection. So we can also try to ensure high data rate transmission, good lighting quality. This is also important. So what are the modulation schemes? For sure is on-off keying and also pulse amplitude modulation. There's another scheme for like pulse width position modulation and also pulse width modulation, carrier-less amplitude and phase modulation, color shift key, and also we have the multi-carrier modulation schemes. So we have the orthogonal frequency division multiplex, it's very well known. We are now also working in this constant envelope OFDM in order to reduce the PRPR. And also we have the generalized frequency division multiplexer and digital subcarrier multiplexer. This moment we are invest more in digital, and these two, constant envelope OFDM, and also this digital subcarrier multiplexing. Why? I'll show later. So what are the main goals for indoor communications? How we can compete with Wi-Fi? This is important because at the end we need to sell it. Okay, so how can we achieve record high bit rates? This is the first step. Is the technology capable of offering good lighting quality and high bit rate? How can these systems be implemented in real telecommunication infrastructure? So these are the three main goals and questions that we should address. Let's go to the first one. How can we achieve the record high bit rates? Okay, so we have been using, for sure, what we need to hear the limit of the channel capacity in order to increase the bit rate and also the distance of transmission. This is very important, using modulation techniques for that. Let me go. And also, we need to optimize, take into account the distance and transmitting information for different frequency bands, because for sure we have limitation in LEDs and lasers, so we need to, using sub-carrier multiplexing and using entropy loading, this one will show, and also bit loading and power loading, we can try to use the most of the spectrum of the laser or LEDs. This is what we've been doing. We also can work in geometric constellation shaping. So as the source, we have the light emitting diodes, for sure. We have the main drawback is the bandwidth. For you have low bandwidth, that typical tens of hundreds of megahertz. But they already been demonstrating some work at high bit rates, up to 20 gigabit per second. Using laser diodes, for sure you have wider bandwidths, can be in a range of few gigahertz for direct modulation, and they also been shown some transmission capacities up to 30 gigabit per second. Okay, but can you do further? Can you go increase this bit rate? Again, can you compete with Wi-Fi? This is what my question. So we have been developing some experimental setup using RGB. So we're transmitting the three colors. So we are using sub-carrier multiplexing to take the most advantage of all the bandwidths. And after, we drive each source to RGB lasers. So we have the red, blue, and green. We want to use diffuse light, because this is important, because you want diffuse light, you don't want to do beam steering. So you want to be a diffuse like this light. So this is one of the setups. So we have here the three lasers, the green, red, and blue. And also we have some dichroic mirrors to make the mix. And also here you have the diffuser, because you want to diffuse the light. So this is a transmitter side. We have the optical channel that we can change the distance. And also we have at the receiver side. So at the receiver side we test using avalanche photodiodes and pinned photodiodes, and also using a low noise amplifier. Again, you need some dichroic mirrors to separate the three colors. And after we are using a real-time oscilloscope for this demonstration and to get the information. And also all the offline DSP processing. So in this case, these are three APDs from Hamamatsu. So one you are using for, again, for blue, green, and red. And also you can see the part of the dichroic mirrors. By using entropy loading, so again, using entropy loading with digital sub-carrier multiplexing, we can try optimize the bit rate and also the distance. So how it works, so depends on the signal noise ratio for each subcarrier, we can define the number of bits per symbol that we can transmit. So this is what we can try to optimize, basically. So by this way, you can try to use all the bandwidth that's available. For sure, where you have, I'll show, in some parts where you have less, the frequency response is down, we can decrease the number of bits per symbol. So we did this for for the three colors, for red, green, and blue. Again, what we have here, it's the entropy, bits per symbol, and these are the subcarrier frequencies. So for each subcarrier, you can calculate the signal noise rate, and you can check for error correction what will be the maximum capacity that you can achieve after for correction. So we test for pin and APD, and due to the bandwidth also the pin for 50 centimeters of distance, for sure the pin have better performance, and you can achieve 45 gigabit per second. Okay, since the distance is increasing, okay, the capacity will be decreased, but at the end, due to more sensitivity of the APD, for 2 meters, you can get more than 25 gigabit per second. And this is not optimized. I think there's still room for optimize the bit rates. But if you compare, so you can consider that the APD is the better option for after 175 centimeters. But if you compare with the state of the art and what we achieve in our lab, I think we get the higher results. And this is what we show this at IOPC 2023. So you can achieve very good high bit rates. But I think, as I told you, there's still room for improvement. Is this technology capable of offering good light quality and high bit rate? Okay, if you are using lighting, you also need to adapt the color, take into account the environment. And this is what we've been doing. So you need to do communication performance optimization, but also you should do the lighting metrics optimization, if you want that should be using also for lighting. And so for different temperature of colors, we try to optimize the bit rate, taking into account the lasers that we have it. And this is what we did by changing the currents of the lasers and also measuring all the temperature. And this is what we achieve. You can achieve the bit rate as a function of what will be the environment if you are using for industrial lighting, or if you're using hotels and so on, or the public light illumination. These are some examples that we Why the change with the bit rate? Because also we are changing the current of lasers for producing the color, the temperature color that you like it. But for sure it can work, but also there's all room for optimization. But also very important is the field of view, okay? Because as I told you, we want diffuse light. You need a field of view. So how field of view can get in by this process? You can also get a quite constant bit rate for a total angular width of approximately 25 degrees. So this is what we've been measuring the field of view also as a function of the bit rate. For sure, after 25 degrees, we have a big drop. So what we did, you need several lightnings if you want to illuminate a room and also for transmission. So for an aperture of 30 degrees, your bit rate is still within 80% of its maximum value. And this was one work by Professor Jean-Paul, the present here. So what he did, so he showed also for different distribution of luminaire, show what will be the maximum capacity and also how we can get the signal noise ratio, taking into account the distribution of the lighting. This is done by LED. I think now we need to do for lasers. I think it will be also very good if you can do this, also this collaboration. And so my last question, how can this system be implemented in a real telecommunication infrastructure? How we can do the conversion between wired and wireless? So this also has been studied. So how we can do the VLC interface with the fiber in order to connect to the fiber. So we've been studying different schemes. For sure, direct conversion is not feasible. So we need to find another alternatives. So one first option it's optical multiplexing approach, so we are using WDM. It's quite simple. So it is WDM-based approach. We have 3 infrared wavelengths in a single fiber, each associated each RGB component. So this has also been working. So we have the transmission. This is enough from RGB. You have here the lasers for RGB, and also MUX fiber, and also we have the MUX, and also for each RGB in VLC channel. And also you do the inverse. Okay, there's another project is also using subcarrier multiplexing. So what you call electrical multiplexing approach. How it works? So our idea using different frequency regions, subcarriers, F1, F2, F3 for each color. So, and after, what we do, just using by filtering, okay, one baseband, other is set in F1 and F2. So by this approach, okay, so you are not using WDM, it's more spectral efficient in terms of transmission. So we tested 2 options. Also, we implement this in real time in RF SOC. So this is the first approach, or using second approach, or using subcarrier. Again, you have here digital subcarrier multiplexing. We are creating each band. So the idea also is using very low cost transmission and receiving. So I'm using direct modulated lasers. At the other side, we have the pin, and also we are using here RF SOC to remove, to filter each subcarrier and also do the down conversion. So after you can get the 3 colors in baseband. There's an approach using WDM, conventional WDM, using 3 lasers for each wavelength and transmitting in a fiber. We compare the 2 approaches. There are some pros and cons, but anyway, in terms of performance, they are similar. Okay, so they have a similar performance. So what we have here is optical attenuation of the fiber, the bit rate they can achieve. Okay, you don't have the high capacity that I show you because you are using very low cost DML, and also you have also RF SOC is also limited in terms of bandwidth. Anyway, but you can get approximately 10 gigabit per second at 20 kilometers of fiber. So we also been studying, and this also one work also with the University of Luminance, that we have been also as a postdoc, sometime also in Aveiro and Coimbra. So also the idea here was to join optical wireless communication localization. And we also show this that it can work very well to have, and also using different materials, you can also have a very high resolution sensing. My question now, but can you get commercial products? Okay, for sure there are some already, but also using infrared, some products already available from Wi-Fi and also from the some products, commercial products, but my only question that the bandwidth that we are achieving now for download and upload, they are still very low compared with other radio access technologies, and also the cost is quite high. So, okay, for sure you have always a niche for this, for where we need security. This is one of niche, and also maybe also in some hospitals and so on. So, but for common use, it's still not a very good solution in terms of cost and also in performance. But anyway, we already showed that you can go up to 40 gigabit per second. And also there is also the idea from its Wi-Fi at home. Anyway, they already have some downlighters that are compatible with GU10. Anyway, but it's still a high-cost solution. And my question is, can we compete with Wi-Fi and future with Wi-Fi 8 that is coming? Wi-Fi 7 and 8 will have the same bit rate. Theoretically, the capacity of Wi-Fi is 23 gigabit per second, and I think Wi-Fi 8 will be the same. But if you could try to go to Amazon and so on, and you try to find some USB dongles, we can find the cost less than 40 euros. And this for 6.5 gigabit per second. So I think we're still far from competing. Anyway, but I show you that it's possible to go high bit rates and also can try to reduce the cost. Anyway, there's another approach for using visible light communication. For sure, underwater communication, it's a very good approach. It's much better than RF for transmitting. And I think this still that can be very well explored. And also, for sure, for defense communication, this is very important because in war situations, we need radio silence in order that the enemy can discover. So for sure here the VLC and the free space optics can be very good option. So this is also being tried to use in these war scenarios. So this is what I want to show from indoor. Let's go to outdoor, okay? In terms of free space optics. So what are the main goals for outdoor communication? Can you achieve fiber-like capacity of waves? Can you achieve the same capacity that we have in fiber? Is the FSO technology capable of offering good quality of service? Good question, okay? How can this system be implemented in real telecommunication infrastructure? The questions are always the similar, okay? But now it's a further step because now we want to achieve the same capacity that we have in fiber. Okay, so let's go. For sure, today we have already very pluggable current receivers. And the cost they become decreasing. So now we can have pluggable current receivers for 400 and also there's coming 800. And in future 1.6 tera. So, but what is the beautiful here? The beautiful here that you can make a seamless between wired and wireless with very, very broadband. You cannot do this in terahertz, for sure. Why? Because you're just using optical collimators. And optical collimators, you have very huge bandwidth. So optical collimators perform a seamless fiber-to-air conversion. So you don't need for electrical to optical electrical conversion. It's not necessary. So you can have transparency in terms of bit rate and modulation. And also you have full fiber bandwidth is preserved. So this is the beauty of using optical collimators. So it can be compatible with WDM. So this is you can use different wavelengths, and also you can transmit using the collimators and free space optics. So this only so show this is all C-band, and this is the attenuation that we are getting. Okay, so we have approximately 1.5 dBs in all C-bands. So we can also use all these C-band for transmission. And what are the main advantages of free space optics? So, and also it's very good because for free space, 1550 nanometers, it's working very well. And this is very good for us. So we can use the same wavelength that we are using for fiber. So we can use the same fiber components. They are usually very low cost. So all driving electrons are in baseband, in terahertz node. You need mixers, up conversion, down conversion, so on. So here it's baseband, and I think you have optical amplifiers. Optical amplifiers you can amplify in huge bandwidth with very, very low noise. In terahertz you cannot do it. So there are also unparalleled wireless transmission, and also in top you have also the physical layer security, and also you have virtual unlimited spatial division multiplexing. Okay, another thing very important. Until now, it's unlicensed frequency bands. So, nevertheless, so we have widespread adoption. We have some critical challenge. What are the challenge? The impact of turbulence on link power budget is still difficult to mitigate, and also impact of pointing errors. We need to also compensate. So we need to improve link capacity and reliability. And this is very important because this is also very good for us because there are a lot of challenges that we can address, and I'll try to solve it. So my further question is this technology capable of offering good quality of service? Okay. One problem that I show you, we have the turbulence, okay? So we have the turbulence, and this, what will cause the turbulence can cause beam wandering, and also the scintillation. At the end, okay, you have a wavefront distortion. Question, can you compensate this? So what can be done to mitigate these effects? You can for sure using adaptive optics. It's a very nice field. And also we have, I'll show also enhanced field, fiber coupling. This is also can improve a lot. In terms of DSP, it's a bad news. Okay, the DSP cannot remove these effects, but the good news, okay, DSP should be used to reduce these impairments. So this is what we've been working. Okay, so we've been studying. First, what we need to study is modeling. The transmission, this is what we've done in 2021, in August, for several days, and you can see the receiver optical power during the day and night. Probably here there's some problem of condensation in the lens. Anyway, but we have this kind of fading, okay, and this is what we need to compensate. So, for sure, this is again the measurement received power. So we have this kind of the impairments, but we can divide into one is the fast fading and the slow fading. The fast fading mainly from atmospheric turbulence, but the good news and which is good, there are some coherencing times between 1 and 10 milliseconds. This is very good because in 1 millisecond you can transmit a lot of information and you can predict the channel. And also we have the slow fading, okay, can result from weather change, point errors, and so on. So there are some, if you make some autocorrelation, so we can estimate the channel. That is about the ideal FSO channel estimation will be able to model both effects to accurately predict the channel state. Okay, so now we need to, okay, sometimes it's difficult to go outside and find all the wind conditions. So we're using wind tunnel, and here in wind tunnel we put here the collimators, and after for different wind velocities we try to see what will be the influence of turbulence, but it didn't work very well. Did some work, but we developed atmospheric chamber. How we did? We put some heaters. These are 2 heaters that we can control the rotation and temperature, and by this way it has been working very well, and also we can add also later the fog. So again, we have here the collimators outside. Now we have two of these atmospheric channel, and for sure by changing the temperature, control the temperature of the chamber, we can emulate several kinds of turbulence. So this is what we done. This is one example. So again, from receiving power, what we have here is the temperature that's been increasing. Okay, when the temperature is increasing, it's easy to see that due to turbulence, you have more fading. Okay, so for sure, now we have several models. One is the gamma model, and also we can compare if can get the same probability density function for irradiance, and also that is possible. So by this way, you can characterize the weak turbulence, take into account the rate of variance, the moderate turbulence, and strong turbulence. Anyway, this again outside from sunny weather and rainy weather, not using the schema, this is one before. But now, how we can do an estimator? Okay, we can do the low complex channel estimator. Just this is a moving average. It's very simple to do the estimation, but we can compare the measurement estimate. Again, why you want to estimate? In order to predict the behavior of the channel, but we also study a different approach, adaptive algorithms, and also artificial neural networks. So we can see from here, from normalized mean square error for the difference from moving average, least mean square, recursive least squares, and artificial neural networks. Okay, what is the working better was ANN, okay, but others also, in sometimes, that are more than enough for the channel estimation. So what are the strategies for turbulence mitigation? Okay, we can have transmitter power control. This one, receiver automatic gain, and also gain power control, fiber coupling enhancement, we all show some, MIMO systems, this is going to be, and also adaptive modulation. And also, for me, what is more important also, and this is the cooperative FSO with millimeter wave systems. So first, this is what I'll show again. So we are using this artificial neural network channel estimation, and after we can control the transmitter power if you have a channel estimation. So we did the first test using that. This is in the roof of IT2. So using approximately 50 meters. So we're getting, first we did the training phase and also the test phasing of artificial network. So again, you can show here also compare the moving measure predict with ANN predict. Okay, we are getting for sure less error using artificial neural network. Again, we test this for night and day. It works for slow fading. It didn't work too much for fast fading. Why? Because the problem of the velocity of the estimation, since you are still using MATLAB, so the frequency in this moment was only 20 Hertz, and it's not enough. So it could compensate the slow fading, and you can compensate more than 10 dBs, but for fast fading you need to implement this in FPGA. And I think this will be the next step. Okay, we have different schemes. This is one transmission near of 2 kilometers, 1.8 kilometers, connecting two cities. This was using LoRa, so the idea is to send, we did also a reference, see the power of the reference, and also send again to transmitter, and try to control the power of the transmitter. This also been work, okay, but anyway, you need a feedback link, which sometimes can be difficult. But this is another possibility to compensate, and we show that it's possible to improve the transmission capacity and also improve the reliability. Another optical, for sure, is optical amplification. Why? Because this does not require channel estimation, so we can work as a saturation mode or automatic power control. But for sure, the performance depends on the amplifier response. Here, using the atmospheric chamber for controlling the turbulence. Okay, what you have here, the time. Why the time it's here? Because when you're eating the chamber, you are increasing so this is a slow variation in temperature, so the turbulence is increasing with the time because the temperature inside of the chamber is increasing. Anyway, what I want to show here, without preamplification, okay, you have a very variation of received power. We also test for ADA phase in saturation mode, and also using automatic power control, and also SOA, semiconductor optical amplifier in saturation mode. Anyway, we use this with other schemes, not only with this. This is another problem. For sure, we also study, okay, but if you increase the fiber coupling, how many? 5? Okay. If you're using fiber coupling, can we enhance it? For sure. And so we study standard single mode fiber, multi-mode fiber, few mode fibers, and multi-mode fibers. And again, we can see if you can increase by using the fiber, that coupling to collimator, we can also show that you can reduce the influence of the turbulence. Spatial diversity, for sure. This is on a topic for increasing. Okay, one is using different receivers, but this is a high-cost solution. It's a low complexity, but it's a high-cost solution, and in multiple collimators and receivers. We study different approach. One is using coherent combined device receiver. A single receiver needs dedicated for sure photon integrated circuit, high complexity. And also we have been studying now using few mode fibers and multi-code fibers. And also this is very good to increase the power and also keep the eye safety. Because if you have different links, we can increase the power and keep in the safety of class 1. So this single receiver, low complexity and low cost solution. Okay, but we need receivers with large solutions. So how it works, it's just very simple. So we have one band, we divide in several subcarriers, so take copies, okay? And this for few mode fiber, using photonic lantern. So we are using, this is, so the idea here is using few mode fibers. So you are using different modes. We filter in each fiber, in each mode, we filter one of the modes, okay? Up to couple, send it, and also do subcarrier demultiplex, and also using multi-input, single output, and all the DSP. So again, we test this using our atmospheric chamber. This is without any compensation. We're using standard single mode fiber with few mode fiber, but we're not combining, but when you're using ideal combining, for sure you get less variation. So again, we can show that we can, it's more reliable. In reality, we can increase the reliability a lot. Depends on NGMI threshold, the FAC that we are using, but it can go from 18% to 38%. We did the same approach, not using, but this is using multi-core fibers. So the idea here is using multi-core fibers for doing the same. And also it works quite well. Again, we can get increased quantity, in this case we are using 2 cores, fibers, C1, C7. Again, we can also increase the power and also can be more reliable. And this is what's been showing. This is possible to increase the reliability, and also show this in OFC 2025. Okay, again, probabilistic constellation shaping. This is the best way to go to, so you can adapt the modulation, take the signal noise rating, so, and also we can get improve of 0.8 dBs in terms of signal noise rating. So this is an approach we have been using. So since you have different weather conditions, we can adapt the modulation schemes, take into account the weather conditions, and by this way, we avoid interruption of the signal, so it can go from 400 to 500 gigabits per second. So this, we did the experimental tests. Joint LDPC coding, we also test it. It works also. You can have some improvement on joint LDPC coding. This is another possibility for using. We also show this, that it works. You also doing talking LDPC post-facking, how many iterations you need for LDPC. Again, we did if you're using automatic power control and not, so we also can show that it's possible to increase the reliability and also try to reduce the latency of the number of iterations of LDPC. But for sure, the killer is the fog. So the best for me fog when we have the fog, and also we can control the fog in this chamber. So the idea is that we should join okay, what you can see is just the power for in terms of the humidity, also in terms of fire. But for me, we should also work together. So a millimeter wave to get the minimum bit error rate, about this kind 25 gigabit per second, but we can use the FSO to speed up, to boost. So anyway, but at the end, always you guarantee at the end, if you have dense fog, some quality of service. So for me, this short. Just finish pointing errors. So this is also an issue. We've been also working because small variation in pointing errors, we have a problem. So here we are using particular swarm optimization. It works in order to improve the. We are also using this in the demonstrator now. In the next ECOC, I think it's the, no, it's JLT, it's called for JLT, but also demonstrate. So the idea, transmitting one core, receiving in several cores, and after, by using the receiver cores, we can try align the beam. It worked. And also this one collaboration also with the University of Federal Fluminense. This was also done in Aveiro. So they was using special light modulator and also using artificial network to try align the beam. And also we can show that it's possible to improve it in terms of gain. We can get gain for displacement of 0.5. We can get gain for 34 dBs. But you want like a system plug and play. So because this is so what you are doing here, you are using a camera, a conventional camera, but can also detect infrared. So for using camera for coarse alignment, and also using quadrant detection for fine alignment. Anyway, but I think we still need to improve it because you need 10 minutes for when you put the box to try to find the beam. I think there's still room for improvement. Okay, this is only the first initial approach. After you don't need it to do it, but for first you need for at least it takes 10 minutes to do automatic alignment. Okay. This is implemented in a real-time infrastructure for sure. Now it's been using. This is for free space optics to speed the stock exchange. Because why stock exchange is so important? Because the latency. Who gets the first information can do it first. So for stock exchange, it's very, very important to have a low latency. These have been also been implemented also in this Atara project up to 20 gigabit per second in some African countries to get links very easily. But for sure, for free space optics for space communication, now this is what they're using for Starlink communications. Now Starlink, they're using free space optics, okay? I'll conclude it. Only to show this on our demonstration that we show that this is also done in Aveiro, connect two cities to 1.8 kilometers, and you can got 4 terabit per second capacity. So for sure we can compete with fiber, but terahertz microwaves cannot compete with us, for sure. Okay, so just concluding, for sure we have current technology plus VSO. We have high capacity fiber compatible optical wireless. So we have the challenge point errors and atmospheric turbulence. There are a lot of ways to mitigate it, and this is very challenging for us. We can get high capacity FSO demonstration. We did up to 4 terabit per second. There's still room for improvement. High bit rates is not difficult. It's just increase the number of wavelengths. Anyway, we need to keep. What's more difficult is we need to keep the power. It should be in class 1. And also we can also show in VLC capacity to transmit up to 46 gigabit per second, 50 centimeters, so we can compete with Wi-Fi. And also we'll show some integrated sensing communication. For sure, optical wireless communication will be an important role in future access to networks. Okay, we received the Shortwave Best Paper Award at OFC 2025. Since you are also bringing BRICS, we receive also our Excellent Technical Cooperation Project Award, and now we also receive 2024 Optics Continuous Best Prize. Sorry for my delay. Okay, thank you.
Thank you for the very nice presentation. So many results that you have brought to us. So we have one very short question. No question. Gustavo?
Thanks, Paulo, for this nice talk. So, are you guys tapping into free space quantum communication? And I know you mentioned UFF, right? And they're working on a project that is sending quantum key distribution through a free space link in the Guanabara Bay in Rio. So I wonder if you guys are looking into that too.
We have one project with ESA. We are developing a base station for classic communication and also for classic communication, also in quantum communication. So this is one of the projects also been working with ESA now. We also show this in OFC, the joint also the two using the two. I can send you the paper. I didn't show because I didn't have time, because it's the classic and quantum. This is possible, and we already show. I can send you the paper. It was last OFC. Okay, so but it's possible, and also it's very challenging, and this is our next step. But we can demonstrate some part, but not from ground to satellite.
Okay, Paulo, thank you. Let's thank Paulo again. Okay.
And thank you very much for the invitation to be here.